In my last video, I talked about the framework of my software, but I didn't talk about the Qiskit software that's actually doing the calculations. And I didn't say why those calculations needed to use an approximation either. An approximation, we've got all these fancy computers, why don't we just do it exactly? Well, this video will point out why that just can't happen. There's one atom that we can figure out the exact solution for. That's hydrogen. Well, in a way that kind of makes sense because there's only one electron and one proton. So there's not a lot that we have to figure out. This can be broken into the angular part, which involves theta and phi. You see, these are spherical coordinates. There's 1, 2, 3 coordinates for the three-dimensional space. And this is the good news. These define the SPDF orbital shapes. If you know enough chemistry, this shouldn't be a total surprise. And there's no approximation needed, even for multi-electron atoms. So this part stays the same. This cannot stay the same because when you get multi-electrons, even with hydrogen and helium, where you've got 2 electrons, you've got the repulsion factors between those electrons, and that gives you a complication that has to be approximated. Here's the radial function. N is some kind of constant here that makes this all come out to be the probability of 1. In other words, all the possibilities have to equal 1. Then this thing right here is really important. This exponential, this is really what we're focusing on. And then let me discuss away some of these other things. This is you'll notice that this is a constant that shows up everywhere. It is r over na sub 0. The r is the radius or the radial function, and see, it's even up here in this exponential. This right here is the Laguerre polynomials, which is a special function that demonstrates what the wave function looks like. So this is pretty complicated or very complicated. So what I'm going to do is underline a certain part of this that's really important. I want to focus on this character right here. This is what we're going to use in our approximation. This becomes very important. Notice what happens as r gets very large. As r gets very large, then this whole thing tends towards 0 because of the negative exponent. So notice the only thing that I brought over from the last page was this exponential, because that's what we're going to use for our approximation. Seems kind of weird that we throw all that other stuff out, but let's just keep moving along. Here's the devil in the details. As soon as we add one other electron, then we get into this situation with the Hamiltonian, which the Hamiltonian describes the energy. Here's the kinetic energy for electron 1, electron 2, the potential energy for electron 1, electron 2. Notice that's dependent upon the distance from the nucleus. And then we get into this thing where the distance between the 2 electrons, the distance between electron 1 and 2, and we factor in this repulsion. Notice these are attraction to the nucleus, so these are minus. This is positive, so this is a repulsion of one electron with the other. So it's this thing right here that really throws the perfect solution out the window, and we have to use some approximations. So more on approximation. I think you'll notice that, let's see if I try to point to it. If you notice up in this corner, I've got something behavioral nature of the Hamiltonian. In other words, it's got that exponential in there. And then I've got this other thing saying the minimal basis for acceptable accuracy. Now the basis, if you notice, it involves a summation of exponentials. And it's been determined, or it turns out, that using an r squared term rather than an r term actually gives you a way of using a product theorem. So that if you multiply two of these things together, you end up getting the same type of thing. And this thing is called a Gaussian. Now, the Gaussian is what's used as the approximation method in our quantum computing software. And that's where I'm headed next, is to walk through that software and see where all this stuff pulls together.